Welcome, everyone. We will wait as usual. I'll just wait like 3 minutes and then we will get started. So in like 2:03 through 2:04, we start with the session for today. All right, guys, let's get started. Uh, welcome everyone. Let me just quickly do a brief introduction for everyone who hasn't been to yesterday's session. So just a quick brief intro about myself. So my name is Marin Sipek. I come from Croatia originally. I have been studying here in the Netherlands for 4 years. So this is my fourth year, or 3 years. This is my fourth year. I'm just gonna keep this brief because I see some names that I've already seen. So I graduated this year or last year, this summer, and I got my bachelor's degree in business and business economics, and currently doing a master's in business and analytics and management, both at the Erasmus University in Rotterdam. So I was at the Erasmus School of Economics, and now I'm at the Rotterdam School of Management. Both last year and this year, I'm an honor student, and the year before that, I think, yeah, graduated cum laude. Been tutoring for 3 years with Athena and 6 years in total. Outside of Athena, I also work at a tech startup in their accounting department. And outside of school and work, I enjoy sports such as skiing and football. Well, just a brief intro into what we're going to be doing today. So this is a free session, of course. This isn't a paid session. Today we're just going to be covering one topic, and that's going to be, as you saw, hypothesis testing. So we're going to be covering hypothesis testing just to show you guys basically how I teach, what the style of my teaching is. Do you like it? Do you not like it? To give you like a sneak peek into how Athena works. Now, before I do get started with the rest of the stuff, let me just quickly give you the WhatsApp link. So if you're not in the WhatsApp group, scan this QR code. It's going to put you in the WhatsApp group. There, I'm going to send the slide deck. So after we're done with the session, I'm going to send you the slide deck on this link. So in this WhatsApp group. So pretty useful to be in those because then you can, you don't have to ask people, do they have the slides and whatnot. You can just automatically get the slides from the group. Okay. So I'm just going to give you like a minute to join the WhatsApp group. And also, I have been told that I have to tell you guys that the session recording is not available unless you basically announce to the marketing management that you're going to miss the session a couple of days in advance. So the sessions are not actually like on demand. So you have to ask for them before if you know you're not going to be able to attend the session at all. So then you get the recording. So there's no recordings afterwards if you have been on the session. So I just had to put that out there. I've been told that I have to tell you that. Okay. I hope everyone's joined the WhatsApp group. Let me just briefly do a little structure on how we do things here at Athena. So basically it's a three-step process of how we do things. So basically the way it works is we do a little bit of theory every time about any chapter. So now we're going to be talking quite a bit actually. Then we're going to do some examples where I explain how they work. And then lastly, we do a practice question, which is most of the time exam material so that you guys I give you a question and you guys spend some time trying to solve it. And then you get to ask me questions if something isn't clear or something doesn't work. And yeah, basically that's the three-step process that we repeat for every single chapter in our full sessions. Okay, so what are we going to be doing today? So for today, we're doing hypothesis testing, type 1, and type 2 errors, and also if we have the time, we're going to touch upon one sample t-testing. Now, before I jump into that, one last thing would be to tell you guys two things. One thing is I usually, with these 2-hour sessions, like to have a little break in between 2 hours. So at around 3, we do a small break of, say, 5-6 minutes, so just so you guys can, stretch, grab some water, go to the toilet, whatsoever. So basically just so you're prepared. And also one more thing is if you're comfortable with it and if it's possible, turning your cameras on would be a huge benefit to me, simply because I don't get to talk to, like, the interaction process and the process of me talking to you guys just goes that much better. Oh, Thijs, thank you. There we go. First one both days. Basically, yeah, if you're comfortable, if it works, please turn on your cameras. Just makes it easier for me. If not, also perfectly fine if you guys don't. So just that's it. And also about the microphones, I see you're already all on board with that. So I won't spend too much time on it. Just keep your microphones off if you don't want to talk, like say anything. If you do have a question that you want to ask, use the raise hand function on Zoom or ask me in the chat like, yo, I have a question, then I'm going to answer. If I ignore you, like in these situations, then feel free to just unmute and ask me the question anyways. Okay. So I think that's it. If there's any questions regarding any of these things that I've already now said, feel free. Now you can unmute. It's a free-for-all, so just if there are any questions, go ahead. Okay, perfect. So let's talk today about hypothesis testing. So hypothesis testing is basically, so for those of you who have been on yesterday's session, this will sort of build upon what we already talked about yesterday, which was the distributions and everything. So hypothesis testing is basically the thing for which we need all of those distributions and all the theory that we learned yesterday. So everything that we've learned yesterday, we use it just for mainly for hypothesis testing. We don't care about, say, means, medians, modes, distributions whatsoever by themselves, right? They don't give us a conclusive answer to what we want to do by themselves. We need a process which is called hypothesis testing in order to answer some of the questions that we might have. So what is hypothesis testing? So hypothesis testing is a way to determine if there is enough evidence to support some claim about a population that we have chosen, right? So I'll give you a quick example. So you can see here, last year, the average price of a home was $100,000. You want to know if the average price is still the same this year. So you do a research on 100 homes listed online, and you find that the average price of the homes you research was 150,000, right? So let's just stay on this sentence, right? So just on this brief paragraph. So we have a question that needs to be answered, right? So the question is basically, well, what is the average price? So actually, let me backtrack here for a second. We could ask multiple versions of a question here. So we could ask a question, well, is the average price of a home still 100,000? That's one question. Another question would be, is the average price of a home 150,000? That's another question. And let's say a third question would be, is the average price of a home between 100,000 and 150,000? That's a third question. We could also ask the question, well, is the average price of a home less than 100,000 or is it above 150,000? These are all different questions which have various, so based on the question that we're asking, the hypothesis test will be very different, right? So the first thing I need you guys to understand, the basis of a hypothesis test is the question that we're asking, right? So depending on the question that you're asking, that really defines what your process of hypothesis testing is going to be. Okay, so when trying to comprehend basically the idea of hypothesis testing, you need to understand that the first thing and the most important thing is the question, right? So depending on the question, the answer and the process of getting the answer is different. Right. So basically, what we're doing here in hypothesis testing is always we need an assumption. So assumption is sort of a thing that we get from the question, right? So you can think of assumption and question as the same, like maybe not interchangeable, but very similar and connected to each other, right? So they're not the same, but they're basically the assumption stems from the question that you're asking, right? So if your question is, well, is the price of a home over 100,000? Your assumption that you're going to try to disprove is that actually home prices are 100,000, right? So your initial assumption is that, well, last year they were 100,000. So now let's just assume that they still stay 100,000. So that's the assumption that your testing will try to disprove. So what you need to find as a researcher is you need to observe, you need to collect some data points, and then try to use this evidence and these data points in order to disprove this assumption that you've made, right? So all of the points, data sets that we collected in the previous lecture, we use it to disprove this assumption that we make. So you can see here we collect evidence or evidence, in quotation marks, to disprove the assumption by collecting data from a sample. So we basically are asking a question. In this case, is the price of the homes greater this year? And we need to say why. Why is that so? So this entire chapter is going to explain to us why the price of the homes might actually be greater this year than it was last year. Now, also, another thing that we need to pay attention to, you can see in the question number 2 right here, is that what if the average price you found this year was 101,000? Now is the price of homes greater? Of course, the assumption or the disproving of a assumption is based basically on your data points. So based on what you collect, that's how much you can or you cannot disprove your assumptions. Okay, so just pay some attention to that, but we'll quantify it in a minute. So let's just formalize this entire process of everything I just talked about. So the first thing that we need to say, and the most important part of it, is the null and the alternative hypothesis. So what is the null and the alternative hypothesis? So basically the null hypothesis, we signify it with H0. Now, this, of course, because PowerPoint is a bitch, you can't really write it properly, but the way we actually write it is H with a subscript of 0. Okay, so not H. So don't be writing H0. Don't write H0. Okay, write this. Okay, this is a convention. This is how it's properly written. Whoever tells you that it doesn't matter, don't listen to him. Try to be as accurate as possible in writing these things, because statistics professors and professors that teach courses such as these, a lot of the times really like these conventions, right? So because this process, I mean, this is now just something that's not connected to this to the material directly. I'm just telling you like a life advice. In hypothesis testing, a lot of the times things will be very similar to each other. So these conventions and these standards that are set um, are gonna be very important for grading, right? Because professors sometimes they give like 10 points for a hypothesis testing question, right? So then they will say like, okay, 2 points is going to be like if you correctly notarize your hypothesis, right? So, I mean, it is only 2 points, but it's very stupid to lose these 2 points on an exam just because you miswrote the hypothesis, right? So just pay attention to that. So the null hypothesis, we write it as H0. So that's basically the assumption that we're trying to disprove, or it's the value that is assumed in the question, right? So in the population. In our case, we saw that H0 was basically the value of the homes that was last year, right? So the H0 is basically that the average price of the homes is 100,000. Now, HA, on the other hand, again, written like this, HA, the alternative hypothesis is proposed. It is something that you're proposing or what you're testing or what the assignment tells you that you need to test is what could be different about the assumed population, right? So it's basically the alternative state of facts that you're testing. Now, the thing that we need to pay attention to when we're talking about the HA or the alternative hypothesis is that it can be two-tailed or one-tailed. Now, what does this mean? This means that basically this depends on whether or not your alternative hypothesis is basically stating that you're testing for if something is greater than or less than, or if you're testing whether or not something is not equal to. Okay, so these things right here, just write them down, remember them. I assume you have a formula sheet with your exam if you have an exam, right? I'm pretty sure you have an exam with this. You have a formula sheet. It might have this, it might not have this. Look at this, remember it, and do not forget it like until you finish your education. Okay, like just never forget this in a sense of like right tail tests and left tail tests are basically one tail tests. You can see here the red area, you have only one red area for the left hand so for the right tail and the left tail tests. And for the two tail tests, you're going to have two red areas. For now, we don't know what this means. We're going to explain it a bit later, okay? Just to be as simple as possible, remember it, like write it down, memorize it, don't forget it, okay? It's one of those things. All right, so here is a formalized expression of what we were talking about. So in our case, we are testing whether or not, basically, our assumption is that the mean is 100,000. Now, can someone just remind me how we say this Greek letter? I'm having a huge brain fart. I cannot remember for the life of me how it's said. Is it mu? I think it's mu, right? Mu. Okay, mu. There we go. Yeah. So the mu is equal to 100,000. And then the alternative hypothesis is that the mu or the population mean. Now, remember here, very important, do not write X bar here. So I've seen that so many times there are people will put like, oh, H0 is X bar equals to 100,000. Okay. The professor is just waiting to like take away those points. Can someone tell me why is this wrong? Why is putting X bar here like a cardinal sin of statistics? By the way, when I ask you a question like this, it's a free-for-all. So just unmute. You don't have to raise your hand. You don't have to type up. Like just whoever gets it the first can just tell me the answer.
X bar is for the sample.
Exactly. Good job, Nadine. So X bar is for the sample population. Okay. Sorry, not for the sample population, but for the sample mean, right? So X bar is the sample mean. So sample mean. You're never, never, ever, ever in hypothesis testing. So that's the beauty of hypothesis testing. You're never making causal inferences on the sample that you're getting, but rather you will use whatever you got from your sample to make assumptions about the whole population, right? So what we're doing in this case, we're going out there, we're taking, I don't know, 2,000 ads in a real estate magazine with, house prices. And then based on those 2,000 data points, I'm going to say, well, the average price of a home in the entirety of the Netherlands or in the entirety of Rotterdam or Amsterdam or Tilburg, doesn't matter, whatever I'm doing. That's the average price of all of them, even the ones I haven't measured, right? So just pay close attention to that, right? You're always testing for the population means, not the sample means. You're just using the sample means to get to those, but I'm getting ahead of myself. So population mean. So like we said, HA is that this mu or the population mean is not 100,000. Now, this might be a bit abstract to some people. Why is it now, why is the HA mu is not equal to 100,000? Why is it not mu equals to 150,000, right? So because that was the question that we're getting. See, we can never test like that. We can't be like, oh, well, I want to test if it's this value. No, like statistics isn't that powerful, unfortunately. Like if it is, the world would be a better place, but it's not that powerful. It can only tell you if you're dealing with something that's not a value, right? So it's telling you like, oh, well, it's not 100,000, or it can tell you perhaps it's bigger than 100,000, or it's smaller than 150,000, right? So you cannot really pinpoint onto specific data points, right? I mean, you can, but not with this level of statistics and not this easily, right? That's something that's like advanced stuff. But for now, we just assume that whenever you have a certain value that the examination or the assignment is going to ask you, we always have to use these three expressions. Okay, so we always use these three expressions, never anything else. So there is no testing. So HA, where mu is equal to some value, does not exist. Okay, so this does not exist. Okay, so never write this because you cannot test for it. Okay, so in this case, of course, we already said because it's not equals to, we're dealing with a two-tailed alternative hypothesis. So basically, what does this mean? If we're saying that something is not equal to 100,000, basically what we're saying, well, if it's not 100,000, the value could be, less or it could be bigger than 100,000, right? I'm not really sure. I just know it's not 100,000. I mean, of course, you can already see why this test doesn't really have a lot of applicability in a sense, because, what does this tell you, right? Like, it's not 100,000, sure. Like, there is no, like, I mean, there is an application to it, but it's limited, right? All right. So what are the other possible hypotheses in this case? Alternative hypothesis. We can see here we have the other two where we can test whether or not this mu is bigger than 100,000 or less than 100,000. Now, here in this question, we could put that mu is bigger than 100,000 as well. Okay? So don't if you're thinking about it, it can work as well. So it's down to you what you want to do, right? In this case, it does make sense, but the other one where you say mu is less than 100,000, the test doesn't make sense, right? Because for you want to see if it's 150,000, right? So you want some evidence that's going to support your claim that the average price of the homes could be 150,000. If you prove that the mu is less than 100,000, you haven't proven anything because you think it's 150,000, right? So that test makes no sense for you. All right. Now, let's go to probably the most important thing that we need to understand about hypothesis testing, and this is the significance level. Okay, so now pay close attention. If you don't understand this, of course, if you understand it already, still like revise it. If you don't understand it, open like all of your ears, all of your eyes, because this is like the bread and butter of hypothesis testing. All right, so I'm gonna try and take it as slow as possible. If I'm going too slow, if something isn't clear, let me know. Because this, like, without this, we cannot, like, if you do not perfectly clearly understand this, everything else doesn't make sense. So, what is the significance level? So the significance level is the threshold that we have that is used to determine if there is enough evidence to reject the assumption. So when we say reject the assumption, this means automatically, let me just go back here. That means that so if I have like my significance level is big enough, this means that I will say, well, H0 no longer works, HA good. So I have managed, so that's the point so I've completed my hypothesis testing if I get once I get my significance level. So in the case of, and yeah, so convention about significance levels is we write them as alpha, or so alpha is written as significance level. So these values will usually be quite low. You will get, you see here typical values are 0.1, 0.05, 0.01. These are, I can tell you from experience writing a thesis, these values are like only for your like in assignment, like when you have an exercise, right? In the real world, the significance levels are much higher because most of us are testing bullshit that has nothing like most like when you're doing some research that you've come up with, most of the times you're not going to find a relationship and you're not going to be able to disprove the null hypothesis. But yeah. So in the case that we have some value of a like significance level, so let's say it's 0.05. That is the same thing as having a 95% confidence interval. So if we go back to yesterday's session where we talked about confidence intervals, we said that if you have a 95% confidence interval and you state that so let's say I have a confidence interval and I say, the value of the price is from 101,000 to 110,000. If this confidence interval is 95%, that means I am 95% sure that the real price is between 101,000 and 110,000, right? So given our test that we had, if we say um, that, we only need 95%. So if I choose when I'm doing my exercise, and now, okay, wait, let me just backtrack here for a second. I need to explain something. So in hypothesis testing, significance levels that will be decided that reject the null hypothesis. So the idea is that significance levels, as they become lower and lower, you are more sure of your assumption. Sorry, you're more sure of the results that you're getting. So in the case of a significance level that is 0.01, you are more sure than in the case where you got a significance level of 0.05. Now, uh, just forget about how we get significance level for now. Just assume you have it. The idea here is that we need to have some arbitrary threshold that is given to us by the lecturer, by the academic community, whatever, that is going to be assigned. And after you have reached this significance level, you can safely claim your results as being true. So let me give you some examples. So we are in the economics field, right? So we are in some economics business world of academia, right? For us, the threshold of the significance level is 5%. Because of course, yeah, sure, we deal with like important stuff, but like if we're wrong, like sure, somebody loses a lot of money, right? But nobody's gonna die, right? I mean, in theory. Now, let's go to the medical world. So, medical science and medical research has significance levels of 0.01 or even in some cases 0.005, right? So, when you're doing research in the medical field, like if you're testing new drugs, if you're testing like new like cures and shit, like their convention is 0.01 or even lower. Like I said, like I know I read that like cardiovascular medicine, like cardiovascular medicine that's getting tested, they have significance levels of 0.0025, right? So there is a 0.25% chance that they're wrong. Why is this so? Well, because if you make an assumption in economics and you have a 0.05% significance level, and so you're 5%, there's a 5% chance that what you're saying is wrong. There is that's it's not such a big problem, right? But if you do that with like I don't know, heart medicine, like you probably don't want to be wrong in 5% of the cases, right? Because I mean, it's medicine at the end of the day, right? So that is a convention. So the idea that the significance level has to be at lower than some threshold in order to reject the null hypothesis. Okay. That is given to us. For you, most of the times it's going to be 5%, 2.5, or 10%. Okay. So one of those three, those are the ones that's going to be given, right? And it's going to be 0.05 or 5% in like 90% of the cases. But don't worry, it's always said in the example, in the exercise. If it's not said, a lot of the times it's assumed that it's 5%. Okay. So just remember that. Now, let me get back to the confidence interval. So like we said, we have basically those 5% that we're not sure, and we have the 5% that we are wrong. Now, so you can see here, if your value falls between, so you're 95% sure, so your value is somewhere in here, right? The true value is somewhere in here. Only in 5% of cases, you will have, extreme low outliers and extreme high outliers. Uh, Assuming that perhaps like what I was talking about yesterday, like if you have an earnings report, if I don't know, I'm a CFO and I say to Thijs, like, yo, please do a report for me, like project sales for the next year. If someone did it in 2019, like a sales report for the next year, they probably thought that they were going to be in here, right? But they actually ended up here because of COVID, right? So COVID was an extreme left tail outlier where everything went to shit, like sales plummeted, whatever, right? So that's what happened, right? There you had an outlier, a situation that doesn't really happen a lot of the times, but it happened, right? So we had those 5%. And, Tice could have come to me and said, boss, well, I told you it was 5%. Like, I didn't say 100%, right? So that's the point of confidence intervals. We always leave room for error. Now, uh, based on this, we now go back to one-tailed and two-tailed tests. Now, when we deal with one-tailed tests, this idea of having lower, like extreme low outliers and extreme high outliers goes away. We only now have outliers on the side that we're testing, right? So if we're saying that something is bigger than, we only have outliers on the right-hand tail side, right? So if something is extremely low, if we're testing if something is lower than something, we only have outliers on the side that is higher than extreme high, like extreme high outliers, right? Because all the outliers on the lower side of the tail still reject the null hypothesis, right? So if she asks, like if I ask her now, okay, tell me if sales, like what number do we have to put that it's a 95% like chance that our sales will be lower than this number. And let's say she says 120,000. So only the values. So if we sell, let's say our mean is 100,000. If we sell 30,000, her hypothesis still stands, right? So even though it's an extreme low outlier, it still supports the alternative hypothesis, right? So she doesn't care about those. But if it's a high outlier, if we actually sell 150,000, those she cares about. So we as statisticians take this into account, and then the entire 5% goes into the extremes that we care about. So when we do two-tail tests and we say, okay, I want 5% chance that I'm wrong, what we do is we do, okay, 2.5% chance I want to test for 2.5% chance on the extreme right-hand outliers and 2.5% on the extreme left-hand outliers. Now, when we do one-tail tests, we say, okay, put everything on the left hand or the right hand side. So I want to test for 5% chance that we do extreme high outliers or 5% chance that we do extreme low outliers. Okay. So that's the idea that we're trying to achieve here. You can see here, so larger rejection region on one side when we do one-tail tests and smaller rejection regions on both sides when we do two-tail tests. Okay. Justin says, is it true that you don't need to find more evidence to prove H0? Just only reject or fail to reject? Yes. Yes, Justin. Yes, that is true. And that is one of the things that we need. So that is the reason. So that is the reason why inference is so that's why we don't do causal inference in this chapter. So I need you guys to, okay, so you asked a very good question, and this is something that might not be relevant to the material per se, but it's very important to realize what you're doing. So what you're doing is you're not proving one or the other hypothesis. So you're not proving it. So there's a difference between proving something and saying that something is, right? So what I'm going to say, let's say in this case, so I'm not saying that the average home price is 150,000. I'm simply saying that it's not 100,000, right? So going back to what we said in here. So we cannot put, so this would be proving, right? So this would be like, okay, it's 150,000, I'm sure. So we cannot do that. Like I said, hypothesis testing is not that powerful. We can only like reject an assumption or, say we cannot reject this assumption. So it's, yeah, like hypothesis testing is useful to a degree. So to a degree, it's useful, but then later on, when we want to do other stuff that's, more, um, applicable in the real world, we're going to need more powerful statistical methods. But that's for your master's degree. I'm hoping. I hope it's not for the master's. Which So you guys are doing a pre-master, but for what master's degree? Or is it like, or like for us in our uni, it's like you have to do a pre-master for every master's degree. It's like they have like specific pre-masters, but like is it like an umbrella pre-master or business admin? Okay, okay, okay. All right. All right then. Then for sure you're gonna do some advanced statistics in those. All right. So generally speaking, we don't want to reject H0. And then we choose our trash for masters. Yeah, trust me, you do. Generally speaking, we don't want to reject H0. Well, no, in most cases, as a researcher, you want to reject H0 because a lot of the times, I mean, not a lot of the times, but like almost always, H0 is what you know and HA is what you're assuming. So you as a researcher, you're the smartest person on earth. You're making your thesis, you're writing your paper, and you thought of something, you think that something is, something works, but the assumption is something that is general knowledge. So let's say, I don't know. Let's give a good example. I don't know what would be a good example. Um, oh my God, I'm getting like a brain fart to think of like a real world, something that's like very obvious. Okay, yeah. So you say like, okay, you think that the sky is actually yellow. So you think that the sky is actually yellow when we're all like retards, right? So the general assumption is that the sky or like the earth is round, right? And you think the earth is flat, right? So the general assumption, H0 would be earth is round, right? So everybody thinks that earth is round. So we're all, like everybody, we have the pictures and everything and laws of physics and stuff. So H0 is that the earth is round. Your alternative hypothesis, because you're so smart and you're such a good researcher and academic genius, you think that the earth is actually flat. So for you, you probably want to reject H0, right? You want to gather enough proof that you want to reject H0 and then get that the earth is actually flat, right? So in most cases, you want to reject H0 actually, right? Because H0 is like writing a piece of paper, like, and then having all H0 still stand, you haven't done anything, right? Like, I mean, sure, now we can get into like specifics and we can say like, okay, you've still proven that this like your contribution to the academic community is still that you've shown that this alternative hypothesis doesn't work. But a lot of scientists don't really like that. They want to, be flashy and they want to find something new. So actually you want to reject H0 in most cases. Yeah. Okay. Let's see here. So now we move on to p-values. Okay. So still stay with me. Stay with me. I know I might be annoying and I might be talking a lot and a lot of it's pretty hard or complicated if you're hearing about it for the first time. Please stop me. Like stop me if something is like if you get overwhelmed and you're like, what is this? Stop. Like I'd rather like we have time in this today's class, so we have a little bit of less material, so we're good. So just stop me if you have any questions. So p-values. P-values is basically the descript, like it's a number that quantifies this sentence. What is the probability of the house price actually being 150,000 or greater if we assume that the average price is 100,000? So p-values answer this question. So the p-value is the probability of getting a value that is at least as extreme as what we observed given our assumption. So we have our assumption that is, we assume that it's true, and whatever we got from the observed sample, the p-value tells us, based on this sample, based on this assumption that is true, how likely is it that HA is actually true? So P-values are the way we get significance levels. Okay, so P-values give us our significance levels. So based on those two, they're interchangeable. I will show you. Uh, so you compare this p-value and you get your significance level in order to get your so in order to see if you have, if you have a rejection or not a rejection of H0. Sorry. So you can see here on this picture. So we have a set of possible results. So these are like, this is what we could have gotten, right? Now, we basically know that a certain value, or the value that we want to get, is at, you can see here in this, I'll just look at this picture right here. So our assumption is that 100,000 is true, right? So that is the true value. So that's the mean. It's on the middle, right? So that's our assumption. We actually go out there and we want to see what is the probability of us getting 150,000 of a housing price if the average is 100,000. So that value, that probability, is going to be all the area underneath the cumulative probability. So going back to the probability density function, right? So if we go into here and then we set 150,000, everything that is colored underneath the curve right here is our p-value. If you remember, this area has some probability value attached to it, right? Now this is now you're doing some integrals and whatever, but you have tables, so you don't need to just think about it. Don't think about the maths, right? So if you don't know, like if you're now, like if you're like wheels are turning and you're like, how do I get a number, a probability out of an area? That's integrals. If you know how to do them, perfect. If you don't know how to do them, still good because you have the tables, right? All those statistical tables, those big tables that have all those numbers in them, they give you this thing, right? So they're gonna tell you where, like, based on the point that you're located, what the area is going to be equal to. So now, once we have this p-value, we compare it to our significance level, these two numbers, and then if our p-value ends up being lower than our significance level, we get to reject H0. So let's see this question right here. So let's assume that our housing prices question that we use a significance level of 0.05. We use SPSS, we type in some numbers in there, we do some programming, and we find that the p-value of a one-tailed test that we performed with our data set gives us a p-value of 0.032. Do we reject the H0? Why and why not? So the floor is yours, guys. Nina says, can you not only do two-tailed tests with SPSS? Yes, that's true. But just don't think about it for now. There is a way of mitigating that. Like you can work around that. Don't worry. I think so because the threshold of H0 with lower than or equal to is 0.05. Yes, exactly. So because this p-value is lower than our significance level, basically, what does this mean? Now, so we reject here. But now I want you to just think in a conceptual way. So now I want you to just think about the actual like values. So what does this mean? This means that our p-value basically says, if the so basically what the p-value is telling you this. Now listen. Now this is like once you understand this concept of p-values, hypothesis testing becomes a joke, right? Like, trust me, before you understand this, you're like, it's super hard, but once you understand it, it becomes a joke. So p-values basically state if H0 is true and you still go into the sample and you get this value of 150,000, but the actual, average is 100,000, but you got 150,000 out of the sample. That means you got super lucky. You got all the high prices of the houses, right? The p-value tells you that probability. P-value tells you what is the chance that if the mean is actually 100,000, right? So the true value just so that's in another world. You don't know the true mean, right? So your true mean is 100,000. You went into the sample and you got 150,000 by picking up these numbers. That's the p-value, right? In this case, it's 0.032. So it's 3.2 chance. So you have a 3.2% chance to go into the housing market, collect your sample, get the housing price to be 150,000, and the mean still being 100,000. Now, if this happens, you are, in theory, you would be wrong, right? You would say that the housing price is 150, but it's still actually 100,000. So, since this probability of you being wrong, so saying that the housing price is 150 while it's being 100,000 is lower than the threshold that the assignment gave you. So the assignment told you you are allowed to be at least 5% wrong, right? You come back and you say, I got a result that tells me that there is only a 3.2% chance that I am wrong. The assignment then says, perfect. So your probability is lower than what we allowed you it to be. You can safely claim that the actual average price is not 100,000. Because remember, in all the other cases, so in the 96.8% chances that you go into the population and you get a mean of 150,000, the actual mean will not be 100,000. It will be something else. It will probably be higher, right? It will be 110, 115, 120. Doesn't matter right now. But it's going to be something else that is not 100,000, right? Okay, I want a thumbs up if you understood this, and a thumbs down if you didn't understand what I just said. So let's see, like a quick poll. Just you can use Zoom, guys. You don't have to type it in. Just use the Zoom thing. Like a thumbs up, thumbs down if we're understanding this, or if we don't understand this. Ang says nope. Okay, another nope from Jella. Nadine says yes. An says yes. Okay. Could you explain the difference between p-value and critical region and significance level once more? Sure. So, let's just rewind and explain it one more time because I can understand. I would be super surprised if you all got it from the first get-go. Like, I would think you're all lying to me. So it took me like 2 stats courses to understand this, like for real. So basically, the idea is like this. So I, Marin, go out into the world and, my professor tells me, or like my mom tells me, or whoever knows more about the subject tells me, housing prices are 100,000, right? So the average housing price in Rotterdam is 100,000. And then I say, okay, that's the assumption. And then I say, mom, fuck you. I know I'm smarter than you, mom. Like, I know better. And I'm gonna say, well, I'm gonna prove mom wrong, right? So I'm gonna tell mom, like, housing prices are not 100,000. They're not equal to 100,000. They're something else. I don't know what they are, but they're something else. So what I do is I go on the internet. I go to real estate agents, no matter whatever. I go and I collect data. I go and I say, okay, Sir, how much is this house? Sir, how much is this house? I collect, say, 500 houses. I collect their prices. I get 150,000 out of, so my 500 houses that I've collected have an average price of 150,000. Okay. So now stop for a second. We have two values now. So we have what my mom told me. She said 100,000 for all of the houses in Rotterdam. And I have my value, which says 300 houses, 150,000 euros. Okay. Or dollars, whatever. So those two values I have. Now, I sit down and I go like, okay, now, what is the probability that mom was right and the housing prices was 100,000 actually, even though I got 150? Because it makes sense, right? If I tell you that the housing prices are 100,000 average, and you go out there and you hear prices like 170, 180, 200, 130, 120, 160, you're probably going to be thinking to yourself after like 100 data points, like, this guy's wrong, right? There's no houses under 100,000 at all get going into the sample. Where are all the houses that make the average 100,000, right? That's the question you're asking yourself. And that's the question I'm asking myself when I sit down after I have collected my housing prices. So now I sit down and I'm like, okay, what is actually the probability that I got super lucky when I was collecting my sample, right? I went to all the posh neighborhoods. I got all the rich people on the street. I went to the most expensive real estate agents, right? So what is the probability that I did this? And I'm going to say that what is the probability that I'm going to, like, my research is going to say, you know, average is not 100,000, but I was wrong, right? The actual true average is still 100,000. That's the probability that I'm asking myself, right? Because that's the idea of what I'm asking myself, and that is the p-value. So this number, this probability that even though I collected this data and I made an assumption, which is that, sorry, I rejected my H0 and I got this, some research. What is the probability that it was all false, that it was all wrong? The true mean is still 100,000 out there. So out there, perhaps I didn't go to the poor neighborhoods where the averages are like 50, 60, 70, 80, 30, 40, right? I didn't go to those, right? So I fucked up entirely, right? So what is the probability that I did this? That's the p-value. And this chance that I was wrong, that I mistakenly made the assumption that I rejected the assumption while the assumption was still true, is called the p-value. And this p-value is gotten with this basically the outlier or the even more extreme values than the point that I got. So if I got 150,000, all the distribution to the right-hand side of 150,000 in this case, and the area underneath them is going to be my p-value. Now, let's just go back to my example for a second. So I get 3.2%. So that's the probability that I get, and then I go to my mom and I say, Mom, I'm 3 point, so I'm 96.8% sure that you're wrong. Like, I think like 96.8% sure that your assumption that the average prices are 100,000 is wrong. And then my mom says, I only need you to be 95% sure because I'm not going to be too strict about it because you are still my son. Like 95% sure is like good enough. And then your mom says, "Okay, because you got this data, from now on we change our assumption and we say that the average price is not 100,000." So that's the process start to finish again. Now, any questions here now? How are we doing now? Now, I don't expect you guys to fully grasp this. Like, you're gonna have to hear this a couple of more times, either through me or through your colleagues or through the professor. But like, and don't feel bad about it, okay? Don't feel like, oh my God, like I'm so dumb or whatever. It has to happen, right? You have to hear, like, it's one of those things where you have to hear it a couple of times for it to really click in your head because it's a different way of thinking compared to everything that you've done so far with numbers, right? You haven't thought about numbers this way yet. I mean, Probably you haven't, like if you've had statistics, but for those who haven't, who don't come from quantitative backgrounds, take it easy, take it chill. It's all right.
Just one question. So basically, if we
Go ahead.
say the value is bigger than the p-value, we can say that um, the probability that you're wrong is higher. So we say we cannot trust your assumption. Is that
Yes,
right?
yes.
So the
So
lower the p-value, the better, basically,
yes,
because we can
yes, exactly,
trust what
exactly.
we say.
Yes. So if you were, so in an alternative universe, let's say I come to my mom and I say, you know what, mom, I'm 93% sure that you're right. My mom is gonna say, not enough, son. We still think the average price is 100,000. Because my mom says I need you to be at least 95% sure. Okay. So that's the idea, right? So that's the idea of the significance level. That's why significance levels exist, because there needs to be a limit where we stop and we say, okay, this is where we reject, this is where we don't reject. Okay, now before the break, let me just quickly show you how all of this works in SPSS, right? Because SPSS is the program that we're using here, and we need to know what it's telling us, right? We see those stupid tables, and then we're like, what is this? So basically, here we have a t-test, right? We haven't really talked about t-tests yet. We will, but I mean, I will explain them now in the second part. But basically, and just very quickly, I assume most of you are familiar with t-testing and standardized testing. Or no, just give me like a thumbs down if you don't understand z-testing, t-testing, or testing of any case, like and just standardizing probability distributions, just in general. So how, like, just give me a thumbs down if you don't know how it works. I think we only went, oh, you only did t-testing. Okay, yeah. All right. Yeah, z-testing is the even easier version of t-testing, so that's why I mentioned it. Okay, I will explain it then a bit later, but for now, uh, let's just assume here, so this is our output. So first thing we see here is the mean, right? So that's the expression of our, so that's our like of the sample that we had. This is the mean that we get. This is what I get when I go out into the world and I collect my housing prices. So that's the number. So for me here, it would say 150,000. Standard deviation, standard error mean, of course, are those things that we talked about yesterday, between the values of the mean and the actual values of my sample. Now, next thing, we have the sample test, right? So the test value you can see here is equal to 50 is basically what we're testing against, right? So this is our assumption. So this is H0. H0 is that we get mu is equal to 50. We can see here that we got that X bar is 52.77. Okay, so that's what we got in our assumption, right? In our testing, sorry. Now, next up is the confidence intervals, which tell us basically the significance. So based on our significance level, which we know is 0.05, or we can also say a 95% confidence interval. Same thing as saying significance level of 0.01 or a 99% confidence interval. Okay, those are interchangeable terms. T-test, again, I will explain a bit later, but just assume that this t-test, so we use the t-test to get the value, the p-values. So this number right here, it's only like use is to get p values. And then those p values get compared to significance levels. And then that gives us the answer. Okay. So that's the idea. T-test gets you the p-value. P-value, you compare it to significance levels, and then that gives you reject, not reject, basically. Yeah, you can see here, the SPSS output actually gives you the p-value itself, right? So if you were to do this by hand, you would have to calculate first the t-value, then the t-test value, and then you would need to go into those tables, find the p-value yourself, and then get to all of this. SPSS is a bit more nice because it gives you everything by itself. You can see here, this one already gave you the significance. It says 0.00, right? What does this mean? There's a mom. I'm 100% sure, right? Go. Good job, son. Reject that shit, right? So that's the idea. Okay, yeah, you can see here, reject or not. Of course, I mean, it's pretty obvious that we reject here if the p-value is 0.000, right? So there's like almost a 99.99999% chance that this the value is actually not 50. All right. Yeah, you can see here, same what I just said. All right, for now, let's yeah, this is basically what we just talked about. You know, instead of finding the p-value, we can basically find the specific value for which the p-value would be 5% after it. But honestly, let's do a quick break for now because I wanna revisit this and talk about it a bit more, and I want to give you guys a moment to, you know, catch your breath. So let's take 5 and then come back and we continue with this. All right, let's get back to it, guys. So now going back to p-values. So let's talk about basically critical or rejection regions. So basically what we just talked about. So when when we find basically instead of trying to do like p-values, right? We can find specific points on the data set. Oh wait, Luyao says if there is a significance two-tailed and significance one-tailed, it has two p-values. No, it has one p-value, but the calculation is different. I will talk about we can talk about that a bit later, but I mean I can explain it. So I can just briefly explain it. So in SPSS, someone already asked me what happens because SPSS always gives you two-tailed results. If your test is one-tailed, but so you plug it into SPSS and you need a one-tailed test, but SPSS does everything with two tails, all you have to do is you need to multiply your p-value by 2. Okay? So whatever you got on the two-tailed test, you just do it times 2 and you're going to get your one-tailed test. So if SPSS gives you 0.01, your actual p-value is 0.02. Okay? So write that down, remember it, don't forget it. Like it's one of those things again that we need to remember. Okay, so let's go back here. So if we so instead of finding a p-value, we can find a specific point on the table, on the data set, which will tell us that if we get this, there is a 5% chance or less that we are wrong, right? Whatever we take, right? So if we get a sample, so we can reject this H0 if this value that this threshold value that we observed is more extreme than the start of your critical region. So how does this work? Basically works this way. If I go into my tables, so into the tables that we discussed, and I find a value of say 140,000 in there, and that's exactly on the 5% rejection region. And I say, or in this case, you can see it's written down on the right-hand corner right here. It says, so right here, it says 130,000, right? So if we go back to our example, we go into the table and we find it in the calculations that if we were to find a value in our sample, so if the average of our sample is bigger than 130,000, we can automatically reject, right? So this is just another angle of approaching the answer of reject or not reject. So if it's a bigger than 130,000, you automatically reject, right? So in our case, because we get 150,000, we don't need to go and find the p-value of this 150,000. Rather, we can say, okay, it's bigger than 130, which is, the automatic rejection. We can now safely just say we reject the null hypothesis of the mean being 100,000, right? Now, again, these are two ways of doing things. Most of the times the p-value version is going to be a bit easier because getting this value requires you to go to the tables and do some calculations. But let's not talk about that for now. Let's just assume like I'm unfortunately, guys, I cannot really explain a lot in these 2 hours because it is a free session. I would love to talk to you about everything, but I can only explain so much in these 2 hours. And the rest we're gonna talk about later. So again, this rejection decision is based on where our our sample average is with like comparative to this value that gives us the 5% chance of being wrong. So let's just go here. So this is basically like how do you make a conclusion regarding rejecting H0? Basically in these two ways of doing things. So you can either go through critical regions or you can go through p-values. So if you use critical regions, you will use basically, so when the question doesn't give you a p-value, so the exam tells you to solve everything yourself, you will need to use the table to find the specific location of this critical region. This is basically what I just said. You will then use the test statistic that you got to find the location of your observed data, right? So where your data is located on this basically on the distribution, right? So where is your point? So where is your black arrow? Where is this arrow for you? Now, for p-values, on the other hand, you will simply use the p-value that is given to you by the question, which is the SPSS output on the exam, right? You simply look at the p-value, you say, well, is it better? So is it smaller than 0.05, or is it bigger or equal to 0.05? And then you will know reject or don't reject, right? Again, 0.05 is the baseline in 90% of the exam questions. It's going to be 0.05. Please don't get confused if it's anything else than 0.05. So I hopefully now you understand the concepts behind what we're trying to say. So you're not remembering things automatically, right? So you're not doing things automatically. I don't want you guys to do that because professors know that, right? So they know you guys, like they know the people that want to get fives, sixes, and sevens like just automatically remember stuff and they don't know what they're doing, right? So for the people that want to get the eights and nines and tens, in which I always tutor you guys to get eights, nines, and tens. I will never tutor you to get fives and sixes. Um, you need to understand the concepts, right? So don't get confused. Please don't get confused if the p-value is not 0.05, or if the tail is not two-tailed, or if it's one-tailed, or if the hypothesis, or if the wording is a bit different, or something happens, right? As long as you understand the concept, there is nothing they can do to confuse you, okay? All right, there we go. So just, I need to get that out there. Like we said, we reject the p-value if we're smaller than the significance level. All right, and now everyone's favorite part, which is the practice part, because I get to rest my mouth and you guys get to do something. All right, any questions before I get started here? Yutong says, so critical region is used for t-test. Yes, 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 yes. Okay, so if there's no questions, let's go to the question. A question about t-test. So we want a higher typical value because we want HA to happen more often because we want to prove that HA is right. So I want you to, so I want you to, and I want everyone here to remember, again, I know I say this a lot, but just there's a lot of important things I have to say. In the level that courses such as this one operate, there is no you want, right? So you don't want anything, right? So remember, you don't want anything. And that's the key thing about statistics. You never want to want anything. You simply test what you got, right? So there is no like, oh, I want the HA to be like this. And then if I on the exam, if I get like three reject, so if I have three questions which do not reject the null hypothesis, I must be doing something wrong, right? So it's like, oh, I'm doing something wrong, like I'm not getting a good number, right? That's not how it works, right? You do what is on the exercise. Statistics is not about like you don't uh expect something to happen. You simply observe the data, right? So I mean that's why statistics is not a like a science in of its own, but that's why everyone needs it, right? So that's why when you study psychology, law, medicine, biology, economics, math, everyone needs statistics, but statistics isn't like a science in of itself, right? It does like so we never have to want something to happen. We have our data set, we observe our data set, and we get what we get, right? That's it, right? So you might get a p-value that's 0.00, you might get a p-value that's 0.7, right? Like you don't know, right? So whatever it is your data set is, it's gonna give you what it's gonna give you. Like I can tell you, like I was doing my thesis this summer, and like my first p-values for like my original hypothesis, they were like 0.7, 0.8. It's like, when you get those values, it's when you say like, oh, like, I don't know, the average person is 120 years old, right? It makes no sense, right? But I can't be like, oh, well, I'm gonna tweak the data or something. No, like I'm simply observing with statistics, right? Okay, so let go of the notion that something needs to happen, right? So just don't think about it in that way, right? So you're simply observing the data and like calculating what the data set gives you. Nina says, so we will never have to calculate the p-values ourselves. It will always be given. Okay, so this is something I cannot really answer in a sense that the thing is, I haven't done your course. So I don't know at what level your professors are expecting you to be. My assumption, and this is simply from experience, my assumption would be because this is a business admin course and this is a business admin pre-master, you guys are probably going to get the p-values yourself. If you were doing like economics or econometrics or like quantitative research, you would probably have to get them yourselves. But because you're doing some like a bit more like because you're like you don't really care about stats that much, so you're probably gonna get them. But don't trust me. Like again, disclaimer, don't trust me. Ask your colleagues, ask the people around you. You guys probably know how to answer these questions better than I do. Okay, so just pay attention to that. Tice says, so if p-value is larger than 5%, then we accept null hypothesis. You don't accept null hypothesis. Again, what do you do with it? Ah, you got it. You got it. Come on. Remember, what did I say? You don't reject the null hypothesis. You cannot accept the null hypothesis, right? And neither can you accept the alternative hypothesis, right? So you're never accepting anything, right? You're simply rejecting or not rejecting the null hypothesis, right? So going back to how limited hypothesis testing is, we never truly say, oh, this is, right? So we simply say like this could be or this couldn't be, right? All this other stuff of like accepting goes into other statistical methods, right? So this is like I think of hypothesis testing as like an introductory, like introduction to statistics, right? It's the first thing we all learn, like because it's like statistics is like Legos, right? It's building blocks, right? So you need to understand hypothesis testing, then t-testing, then like regressions, then I don't know, regression discontinuity designs, then causality, Granger, then you have machine learning, and like there's like it all builds on top of each other. And you know, the more you go up, the more complicated it becomes, but it also gives you more explanatory power. So yeah. But yeah, so do you reject or you do not reject. Never write I accept null hypothesis or I don't accept null hypothesis. Like cardinal sin number two. All right, let's see. Questions for you. Now, I will shut up for a second, and you guys just look at the questions. I'm gonna give you like 3-4 minutes per question, and then we can go on. All right, let's see. So answer A, of course, because it's basically telling us what is like the question is simply what is the null and the alternative hypothesis here, right? So we're simply saying what are we trying to prove and what is assumed and what are we trying to prove, right? So pretty simple here because it's asking us then we say that the data is basically asking us, is it different than 50 milligrams, right? So the null hypothesis is that it is 50 milligrams, and if it's different, that means not equals to 50, right? Next question. Let's see. Okay. Let's see. Some are saying A, some are saying D. Okay, so what did I say here, guys? If we have to basically remember what is this. So the two things that are important for us are the significance level and the p values given our decision whether or not we want to reject, or our conclusion whether or not we want to reject or we don't want to reject, right? So the idea here is we look at the significance level and the p values, right? In our case, we have a significance level of 0.1 and we have a p-value of 0.09. In this case, we simply reject because p-value is smaller than 0.1. So D. Okay, so that was hypothesis testing. Hope everyone liked it. Now, let's quickly go over type 1 and type 2 tests, and then we will try and get done with one sample t-testing. We'll see how much we can get through. So type 1 and type 2 errors. Now, if you've been listening to everything I've been saying, type 1 and type 2 errors should be a breeze, right? So they shouldn't provide any confusion at all because they're simply like a formalization of what we already discussed. So type 1 errors or alpha risk or alpha is the probability that the null hypothesis is rejected when it should not have been rejected, and it is decided at the start of the experiment. Can someone tell me what is type 1 error? How do we call it? What is a synonym for type 1 errors? Go, go, go. So we should know it by now, right? So if you read if you read it, you go back through all the terms that we already discussed today, what do we think the type 1 error is called?
False
What is it?
positive?
Sorry?
Is it false positive or double?
Yes, 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 yes. But like using the terms that we already uh like mentioned and described in today's course. So you're all mentioning systematic measurement error, but that's something else. But no, no, no. Just use read the sentence. So if you read this sentence, so just read this sentence and think about it. What did I say this is? So going back to me and my mom. Okay, I don't want you thinking about me and my mom, but for the sake of this exercise, let's think about me and my mom. P-values. That's right. So p-values, or in this case, it's not the p-value, but rather something very close to p-values. Besides like the other thing. The other thing, it's not p-values, it's the thing that we compare p-values to. Come on, someone. I know you. I know I gave you like a tip that should give you the answer now.
Significance level?
Significance. There we go. So significance levels. Type 1 errors are basically the synonym for significance levels. You can see, like another hint is that they're decided at the start of the experiment, right? So basically, type 1 error is when you reject H0, but H0 is actually still true, right? So that's the type 1 error. Type 1 errors are, very bad. I mean, type 2 errors are also pretty bad, but type 1 errors in stats are a bit more bad than type 2 errors, like in the stats that we do. But in real life, they're equally bad, both of them. But never mind for now. What we need to know is that type 1 errors are literally just significance level. And now, if anyone was very keen and looking, they would have noticed that the symbol that we use for type 1 errors is the same symbol. If we go back now here for, back 30 minutes, and we go back to the significance level slide, we write them down as the same symbol, right? So significance level, type 1 errors, it's not it's not a coincidence that they're both written down as alpha, okay? So alpha, type 1 error, or significance level. Next up, we have type 2 errors or beta risk. So that's the probability. It's the exact opposite of a type 1 error, which basically states that it's the probability that we do not reject the null hypothesis when we should have, right? So we should have basically rejected the null hypothesis, but we didn't. So we said, you can see here on this funny little picture, let me just move it a bit, that basically type 1 error is when you tell someone, like you tell to a guy, like you're pregnant, right? When the guy isn't actually pregnant. So And then type 2 error is when to someone who's actually pregnant, you tell them, oh, you're not pregnant, right? So two different situations. Now, type 1 error is preset. Type 2 error, on the other hand, you cannot really touch, right? Type 2 error is a bit more tricky. Type 2 error depends on sample size, distance from the null hypothesis, and also the alpha and standard deviation. Now, the only thing that basically mitigates type 2 errors efficiently, like from a practical sense. So let's say A is given to you by your scientific field. So you cannot touch it, right? So you can't touch A. Standard deviation also just shows up in your data, so you can't change it. Distance from H0 is given to you by your, your assumption of your exercise, so your experiment. So as well, you can't really change your distance from H0, right? Because, that would mean modifying your experiment, which makes it, different. So the only thing that really touches beta is the sample size. So that's the only thing you can touch when you really want to lower your type 2 error levels down. That's why everyone wants to have as big as possible sample size, right? Because everyone wants to mitigate both type 1 and type 2. Type 1 can be mitigated by simply lowering alpha, whilst beta really not so much. And the tricky thing here is that if you lower alpha, sure, you will lower your type 2 error, but it makes your experiment harder to prove, right? So that's the trade-off here, right? So everything, and now this is like going beyond the capacity of the course. But statistics is a game of trade-off. You're always trading something for something else. Like you're trading accuracy for clarity. You're trading clarity for how long it's going to take you to do the course, and so on and so forth. Okay, now see here. This is basically like a graphical representation of what I was just saying. So how to make beta smaller? You can make your alpha become bigger, so your significance level can become bigger. Then you're making a mistake, so you're increasing your chances of making a type 1 error, but you're lowering your chances of making a type 2 error. You can make your sample size go up, so your n becomes bigger. You can you can't really lower your standard deviation. You can try to reduce noise in your sample, but that is very hard. That is now research design. That is like another, like a top, like 100 topics to the left. So I'm not even gonna mention it, how we do that. But let's say that we can somehow magically lower our standard deviation. And the fourth one is if we move away HA further away from H0, then we can lower our type 2 errors. But also if we do that, if we move away our alternative hypothesis, that automatically makes it harder to prove, right? So we understand that it's harder to prove that your HA is bigger than 150,000, then if your HA is that something is bigger than 120,000. If your mean is 100,000, it's much easier to prove that something is bigger than 120 than that it's bigger than 150 if your mean is 100, right? So when you move it, of course, you lower your type 2 error, like probability of type 2 error, but you also lower your, it makes it harder to prove your exercise, right? So your experiment. All right. So you can see here. So since we can decrease basically type 2 error by changing the type 1 error, you can basically decide based on your research what you want to avoid more, right? So it basically means if you're testing, if you remember, I'll just give you like a quick example, which I know my professor gave me when we had this course in year 1. COVID tests. If you remember COVID tests, those bitches had false positives everywhere. Like if you remember, like the first tests, if you remember, they you tested positive for everything. Like everything gave you a positive COVID test, right? So that was a huge type 1 error problem. But if you remember then, I think it was like 6 months or 9 months later, we had that Omicron thing, like the hugely contagious version of COVID. Then those tests didn't work, right? Then we were moving into you tested negative, but you were still contagious, if you remember. We had that thing where the first COVID happened, everybody was testing positive, and then we had the second wave of COVID where people were not testing that much, but everyone was having COVID, right? That was a type 2 error, right? So we had two practical applications of two problems that were happening. So if you were, a test designer in real time, in the first wave, you wanted to focus on minimizing your type 1 error. Then 9 months later, you wanted to make tests that were type 2 error resilient, right? So then if you remember, back in COVID, in the first wave, we were doing mostly those PCR tests, like those big expensive tests. And then later on, we moved over to doing those cheap tests because both like worked better in the two situations. So that's statistics for you in real time. So some nerd in front of a computer was deciding our lives back then, like what we were gonna do with the tests and everything. So yeah, fairly like very interesting. That's what got me into stats when I had my first lecture. All right, let's do some more practice here, and then we move on to the final part, which is going to be the one sample t-testing. I think this one has only one question, so you're good. So let's see. Suppose that you did not reject H0. What possible error could have been made, and what could have been done to prevent it? All right, so everyone's saying D. That's good. So it's definitely a type 2 error. So if we did not reject H0, the only thing that could have happened is that the actual mean wasn't, so we should have rejected H0. So it's not a type 1 error at the start. So we're left with C and D. Now, if we were to decrease significance level, so if it goes from say 0.05 to 0.01, from 0.05 to 0.1, then what would happen? We would actually make the type 2 error less probable, right? So that's not true, right? We would have made the type 2 error more probable. So that's not true, right? That just worsens the situation. So the only thing that we're left off is that we can increase the sample size to lower the type 2 error. Exactly, so type 10, so D. All right, so that's that. We are now left only with one sample t-test, but I would just like to quickly, before you all sort of evaporate on me, because probably some people will leave, I would just like to talk to you for a second about, oh wait, Justin has a question. Justin says, how do you pronounce B like alpha? Maybe I'm really stupid right now, but I don't really understand what you're trying to say. Are you trying to say like what's the Greek letter or like expressed beta? That? Maybe that's what you're trying to say. I think. So if you're asking me how do you basically say like how this is pronounced, this is beta. There's a couple of more of them. There's also like this is sigma. Not sigma as in like all that gen alpha stuff, but like sigma as in the letter. And then what else do we have? We have we're probably not gonna have this one, but that's tau. And okay, so you have alpha, beta, you have gamma as well. This is gamma. And then what else do you have? I don't know what else do you have. I think that's it. Yeah. I mean, there's a couple of them more here, but it doesn't matter. All right. So before I move into the last topic, I just want to spend a couple of minutes just talking about how just to talk about the free and the full sessions. So today you were a part of the free session that we had with Athena. In the full material, we will cover absolutely everything there is to the chapters in this course. So we will cover absolutely all the exam material. We will cover all practice questions based on past exams. We will precisely explain all the topics that you can expect on the exam, not just the ones that were in this free session. And I think the most beneficial part of the full training is the fact that we cover 24/7 WhatsApp aid. So if you guys have any questions, any concerns about the courses or any of the sessions that we did that day or the other day or the day before that, or anything that you're solving at the moment. So perhaps you're practicing for your exam and you have a question, you ask your question in the WhatsApp group, and then I'm there to help you. You can text me in the group, you can text me privately. So I'm going to be the one who's going to be teaching the free extensive course for this class. So basically, whatever you need, you can just text me and ask me. I'm gonna probably gonna explain the question to you. If not momentarily, at the same moment, as soon as I can get to it, right? But I hope I do like to think of myself as having a good track record. So yeah, that's it. If there are any questions you guys might want to ask about the extensive training about Athena, I'm gonna open up the floor. Just I'll try to answer to the best of my knowledge here. Any question? I see a question. So I just ordered the weekly training. So Yup says I just ordered the weekly training, but I just realized I can't make it to the first session. What should I do? So the idea, okay, so if that does happen to you guys, don't worry. So if that does happen when you sign up to the course, you just simply tell the admins of the group chat. You can text me, doesn't matter. I mean, actually it does matter. Like you can text them. They like I'm just gonna pawn it off to them. So just text them to save yourselves time. So just text them that you can make it to the recording. Sorry, you can't make it to the session, you get a recording, right? So if you buy the full course, you get the recordings as long as tell us in advance, okay, like I can't make it, I'm sick, I have class or whatever. You still get what you paid for. So don't worry. Okay, any other questions here or are we good? I think. Let's see. Oh, I have three more questions now. Are we gonna do probabilities? All right, so we're gonna do everything, Tice. So every single thing that's gonna happen in this course is gonna be covered, right? So everything that you can think of is gonna be covered. And like as you can tell, I like to talk. I like to hear myself talk. So everything plus like other stuff is going to be covered, right? Um, where can I find this course? So the course is going to be found on the Athena website. You can probably find it under MRM, full extensive course, has my name written on it. You can't miss it. And I think I have the link somewhere. I will try to find it during this course, and I will give it to you. I also have another question. Is the course enough to pass the exam? So in my opinion, yes. So, I mean, this is again my opinion, but this is based on a lot of courses that I've done, and I've done like work with a lot of different people. Because we specifically target the content that is found on the exams, the return, like investment to return ratio of the time that you're investing here and what you're gonna get in advance, like what you're gonna get for your exam, everything is covered. So in the hours that we don't do there is no filler material. There isn't anything that we don't do that's like, the stuff that the professors put on the presentation and they tell you to read it and then it never shows up on the exam. So we filter all of that stuff out and we just go through the things that we know that's going to show up in your exam so you guys can perform um, best you can. All right, so I think that's it. So I wanna go and do this entire. I think we have time for one side to t-testing. So I will try to give you guys the link by the end of this session. But for now, let's just go through one sample t-testing. All right. So what are t-distributions? So it's a type of normal distribution that we use So normal distribution, if we remember, we basically have to sort of go back to normal distributions, what we discussed before, and what we have sort of in the in the previous course. And the t distribution is basically a specific type of normal distribution you use when the sample size is smaller than 30 or you don't know the population standard deviation. Now, I would just have to say here, most of the times you don't. So this is why t-testing is so like overpowered. Like it's amazing. I love it because you never know the population standard deviation. Almost never do you know it, right? Because if I tell you like go out there and find like the average price of homes, you don't know the standard deviation, right? You're never gonna know it. There is very little populations for which you know the standard deviation. Then you use something called a z-test, right? But in most cases, in 99% of cases, you just use the t-test because you don't know the population standard deviation. There we go. About the link to the course. I have something even better for you guys. I actually just got the slide, so the information. Not only do I have the link for you guys, I actually have a discount as well. So we have 10 times discounts for this course, 12% discount to sign up for the weekly training. QR code is right there. So take 2 minutes, 3 minutes if you want to go for it. Here's the link now. So I'm just going to leave this here for a minute or two, and then I'm going to come back to that thing I was talking about. And also, I'm going to send you the slides as well. All right. I'm confused. I don't know where to put the code. It should be in the checkout. So when you put the course in your cart, you go to checkout. At the bottom where your payment method is, you put the discount code. So like at the very end, you put the discount code, I think. I don't see. I keep saying I think, but I'm like I know that it is like that. See, that's another thing that's gonna like happen to you. That's like when you're doing like when you do too much research, you're just thinking everything. You don't know anything. What's the difference between the super bundle courses and the weekly courses? So the difference is that the bundle includes a practice session as well. So the practice session is just so the weekly courses are just us going through the material. And then practice session is just us sitting and going through exam material. Like we do like 20, 30, 40 exercises of just exam material. And then I will solve all of them. I will give you all the answers and I will explain each of them individually. So that's the difference. So you get an additional session in the bundle. Amazing. Just got the full course. See you then, I guess. All right. So get back to t-testing then. I hope everyone's got this. If you haven't, let me know. All right. So going back to t-distributions. So the main thing that we need to understand about t-distributions is that as the degrees of freedom, or just n-1, you can think of you can think of degrees of freedom as very similar to sample size, okay? So very similar to sample size because it's just n-1, so almost a sample size. So as degrees of freedom or sample size increase, the distribution becomes more and more close to normal distributions, and it's almost identical after you get past the point of n equals 30, right? Now, this is because of a thing called the central limit theorem, where the distribution of a sample variable approximates a normal distribution as the sample size becomes larger. So you can see this in this picture right here. So you can see this is a distribution when you have only one thing in the sample, or like one data point in the sample. Here, when you have 3, here when you have 8, when you have 20, and this is like your normal distribution right here. So you can see like if you got to like 100, it's probably going to follow the standard normal distribution. That's why we can use the t-distribution for these things, even though we don't know the population standard deviation. Okay, so here is basically just some assumptions and some like conditions that we need to do for validity of a t-test. So if your sample has to be randomly selected, your population standard deviation has to be known, Your sample size has to be, so if it is smaller than 30, but we know that the sample is normally distributed, the sample is not normally distributed, but it is larger than 30. So all of these case studies, like all of these case scenarios, basically constitute a valid t-test. Now, if a t-test is not valid if your sample is not randomly selected, if your population standard deviation is known, then in that case you use a z-test. Or if your sample size is smaller than 30 and your samples are not normally distributed. What do you do in that case? So there's a couple of things that we can do. We can do some transformation. We can do some parametric test. We can do some bootstrapping. Now, all of these are pretty irrelevant for you guys because you guys don't have to use them. Most of the times you're just gonna end up in this, like in these four scenarios, right? So this is like advanced stuff. How do we turn an invalid test into a valid test for? So for now, for us, we just need to know, we simply need to know the theory, what constitutes a valid test and what is an invalid test, but the conversion of one to the other, not really. Okay, now, again, final thing I promise where you need to really focus for me. So t-statistic, what is a t-statistic? So t-statistic is basically a number. We saw that it was like 2.7, 2.8, 3.1, whatever. It is a value that tells you how many standard deviations the value that you got is away from the mean. Okay? Just remember, like, just think about that for a second. I need you to think about that. And I need you to go back to that picture that we had before. So yesterday, if you remember that picture where we had that bell curve, we had that um, we had the mean, and we had those values of the standard deviations. You remember SD1, then you had 2 times SD, then you had again minus SD, and you had 2 minus SD. If you remember those, this is basically a graphical representation of this. So how many standard deviation is the value away from the mean? If your value has a t-value, so a t-score of 1.5, it is located exactly here. Okay, so this value is t equals 1.5. Okay, now in order to find this t-score, which of course measures how many standard deviations we are away, we have to use the formula that is found here above. So it's t equals x bar minus c divided by s divided by square root of n. Here, this c is basically the mu or the population mean. So the assumed population mean that you have, right? So whatever it is that this mean right here is. So c, I don't know why they put it as c. Usually it's given as mu, right? So this can also be mu, right? So same thing, okay? Remember the formula. Even though it's on your formula sheet, I truly strongly recommend you learn it by heart. Like I simply like it's just like so used, like so widely used that you need to like it's much easier to know it by heart. Okay, now let's look at basically confidence intervals with t-scores. So we already talked about what confidence intervals are, so I don't want to spend much time on it. But we already said how they work, when we reject, when do we not reject. So we can also use t-scores in order to get confidence intervals. So to get a confidence interval that is 95% of some value, right? So of some sample that we have, we can say so what we do is we use the sample mean. So we have it here. So sample mean, so whatever we got out of our sample, plus minus the t-score. Now this t right here in confidence interval is very specific. This is your significance level. So this is your significance level t-score, okay? Times your standard deviation or your sample standard deviation divided by square root of n. Okay, now what is this significance level t-score mean? Now, this is one of those things, again, which I would really, really strongly recommend that you remember the values that every single significance level that we use is. So we usually deal with 90% confidence intervals, so significance levels of 0.1, 0.05, and 0.01. Or, of course, if they are two-tailed, we need to divide this percentages into two. So if they're two-tailed, they're, of course, going to be 0.05. And then this one is 0.025, and this one is 0.005. Okay? Just so we have these three values that are given to us. I mean, we have basically how many specific ones do we have? We have 1, 2, 3, 4, 5. The most common ones that we use are 0.05 and 0.1, and then sometimes 0.01. Now, those values are found in the tables, and they can be basically like you will almost always have them written out, okay? But the most important thing I always like to tell students, T of 0.1 is approximately 1.64, and T of 0.05 is approximately 1.96. Okay? So those are the values of these T-scores, and I would like you will, I mean, I don't even have to tell you guys this, but once you start practicing these questions, you will see the same numbers showing up, and you will remember them like by heart automatically by yourself. I don't even need to tell you this. But what needs to be said is that these values are found in the tables, in the statistical tables that are given to us by the examiners, okay? So these numbers are not something that we need to calculate. We can find them by ourselves in the tables, okay? So the significance level T-scores are found and given by the exercise and can be found in the tables. Okay, now let's try to solve an exercise together, okay? So now we do one last thing, which is we're just going to go through an entire hypothesis test question ourselves. So I'm going to try and please don't leave. I see some people already leaving. Please don't leave. Let's just go through this and then we're done. Okay. So question. Currently, people assume that the average height is 175 centimeters. However, I think that the average height is higher. So I randomly collect average of 100 people. The data I collected about heights resulted in a sample mean of 180 with a standard deviation of 16. What conclusions should I draw about the population if my significance level is 0.05? Now, you see here, you have basically like a step-by-step guide on how you should do things. So the first thing we do is we set up our hypothesis, our null and our alternative. So our null is that the average is 175, while our alternative is that it's higher. So we just say mu is bigger than 175. Now, I'm going to go pretty fast-paced. So if there's questions, unmute and ask. You don't have to raise your hands now. Question 2, is this a one-tailed or a two-tailed test? In this case, because we're dealing with just bigger than, it's a one-tailed test. Question 3 says, please find alpha, S, and N. Now, alpha, we already have significance level of 0.05, very obvious. N is your sample size, which is 100, and your sample standard deviation is also given, which is 16. Second, now, next question is basically, so same question. We need to now do a t-test of all of this data that we already have. We have to, of course, explain why do we use the t-test. Why? Because we only have the sample standard deviation, right? So we only have the standard deviation of the sample, right? We don't have the population standard deviation. And also our sample is bigger than 30, so we can do that. And additionally, the sample is randomly selected because we know this from here. So all of the conditions for a t-test are valid and we can use it. Okay, now we calculate and interpret the appropriate test statistic. Now, we calculate the test statistic, which we get by, plugging in all the values that are given to us. So we have X bar, we have C or mu, we have our S, and we have our N. We calculate it and we get 3.125. Now, what does this mean? This means that 180 is around 3.125 standard errors away from 175, meaning that the difference between 175 and 180 is around 3 times the usual difference between samples. Okay, now this doesn't mean that much to us, but what we need to do is now we need to ask ourselves, do we reject or do we not reject based on the p-value of the critical region? Now, we have our t, we go into our table, and we backtrack and we find the value that was given to us. Okay, so the first thing that we need to do is we first need to find the rejection value of rejection. So the t value of the significance level. So that's the t I was showing you, the specific t. The way we usually notarize this is by having, t and a little asterisk above. So that's the critical value. Okay. We find the critical value based on the significance level. So we go into our one-tail test. We see that alpha is 0.05 for our degrees of freedom, which is for us 100. We go into here and we find it. So it's 1.66. So for us, the T critical is 1.66. Now, we have our test score or our T at 3.125. Since this T is bigger than our T critical, that is a condition for rejection. Now, I can go more into depth for this, but I won't because we don't have the time. For now, just to close off this session, we need to remember that if T that we got is bigger than T critical, reject. If T is less than T critical, reject. No. Okay. Just gonna keep it at that. So because we have 3.125 and the significance or the critical value is 1.66, you can see here, we reject H0. So because of that, our final answer can be because we have found sufficient evidence to reject the null hypothesis. Okay, so you can see here, given the sample and the significance level, there is sufficient evidence to suggest that the mean height of the population is greater than 175 centimeters. All right, so that is it, guys. Any questions here? But please, please, please don't leave yet. I need you for just one more thing. Just please ask questions. Can we go over this more over this next time? Yes. Yes, we will. We will cover this much more extensively. I just don't have the time with me right now. I usually have like 3-4 hour sessions. So unfortunately, I would love to talk to you more about this, but I just don't have the time. All right. Before you guys leave, thank you all so much for coming today. Thank you for hanging out with me. Thank you for listening to me. I really hope you learned something. If you haven't learned something, that you revised something. I hope I was good enough explaining this stuff. I hope so, I guess. I would just like to ask you before you leave, if you could fill out the evaluation form found on this QR code. It's literally like a minute or 2 minutes for you guys, and it means a lot to me and to us as a team to just see how we're doing. Can we improve on something? Can we not improve on something? Are we doing good? Are we doing bad? And that's it. Again, thank you so much for coming. Once again, hope to see as much as many of you in the sessions that follow. And yeah, once you filled out the evaluation form, you guys are free to leave if you wish. If not, if you have any more questions, I'm gonna be here. I can ask you some questions. No, I can't. I'm not gonna ask you questions. I can answer some questions if you need. I wanted to get the super bundle, but the dates were different for the classes, so I got weekly. Is that accurate? Tice, that's a good question. I can okay, you know what? Text me on WhatsApp. You probably have my number. I'm the admin. Just text me on WhatsApp, repeat that message to me, and I'll see what I can do about that concern. Okay? All right. Thank you, everyone. Yeah, that's me. That's me. Yeah. Plus 385. See you all. Bye bye. Enjoy your day.